Welcome all dear friends. I am Dr. Smriti Dwivedi going to discuss about the infrared spectroscopy in this session. As you all gone through the electromagnetic radiations and spectrum in which the spectroscopy depends. Spectroscopy is the interaction of matter with electromagnetic radiation. So, we are going to discuss about the IR spectroscopy. In this session, earlier you have studied about the UV visible spectroscopy, means ultraviolet visible spectroscopy. With the help of UV visible spectroscopy, you can determine the double bond and conjugated double bond present in a given organic compound. With the help of IR spectroscopy, you are able to determine the different types of functional group in a compound. You can able to calculate the vibrational frequency of bond and force constant. You can also understand the fingerprint region that can be used when comparing samples. Topics we are going to discuss here is theory of IR, molecular vibrations, fundamental vibrations and selection rules. First of all, we know what is the range of IR spectroscopy. IR generally deals with the interaction of infrared radiation with matter. The IR spectrum of compound can provide important information about its chemical nature and molecular structure. Most commonly, the spectrum is obtained by measuring the absorption of IR radiation. Widely applied in the analysis of organic material, it is also useful for polyatomic inorganic molecules and for organometallic compounds. IR radiation is in the range of 12,500 to 50 per centimeter. The absorption in the IR radiation can be expressed either in terms of wavelength or wave number. Mostly IR spectra of organic compounds are plotted as percentage transmittance against wave number. There are three regions in IR spectra. First is near infrared, second is mid infrared and third is far infrared. The first region is from 1280 to 4000 centimeter inverse. This region is poor in specific absorption, consists of overtones and combination bands resulting from vibrations in the mid IR region of the spectrum. The second region is mid infrared. The range is from 4000 to 400 centimeter inverse and it provides the structural information of most of the organic compound. The third region is far infrared. The range is from 400 to 33 centimeter inverse. This region has been very less investigated than the other two regions, but it has been used for the determination of the inorganic molecules. You have in the diagram you have seen the spectra of IR. It is generally plotted against the transmitters and against the wave number. Now come to the theory part of IR spectroscopy, on which theory it is based, how absorption created in the IR we can discuss here with the help of going through the theory of IR. Absorption in the IR region is due to the changes in the vibrational and rotational levels. When radiations with frequency range less than 100 per centimeter are absorbed, molecular rotation takes place in the substance. As the absorption is quantized, discrete lines are formed in the spectrum due to the molecular rotation. But molecular vibrations takes place or set in when more energetic radiation in the range of 10 to the power 4 to 10 to the power 5 centimeter are passed through the sample of the substance. The absorption causing molecular vibration is also quantized. Clearly, a single vibrational energy change is accompanied by large number of rotational energy changes. It means when vibration takes place, it also accompanies the rotational changes also takes place in the molecule. Thus, the vibrational spectra appear as a vibrational rotational band. In the IR spectroscopy, the absorbed energy brings about predominant changes in the vibrational energies, which depends on three factors. First, it depends on the masses of the atoms present in a molecule. Second thing, it also depends on the strength of the bond, and third, it is depend on the arrangement of atoms within the molecule. When we are going to discuss about the theory of IR, this IR is very important for determination of the number of functional group in a compound. We can easily differentiate between the different compounds on the basis of their IR spectra, but there is one limitation of IR spectroscopy is that we cannot differentiate two enantiomers on the basis of IR. Now, when IR radiation rays fall on a molecule's molecular vibrations takes place. Means when IR radiation is passed through the sample, vibrational and rotational changes, energies of the molecules are increased and two kinds of fundamental vibrations takes place. One is stretching vibration and other is bending vibration. In the case of stretching vibration, the distance between two atoms with respect to central atom increases or decreases, that is, there is change in their bond length, but there is no change in their bond angle. While in the case of bending vibrations are the vibration which leads to the change in their bond angle, while the bond length remains the same. Out of these two vibrations, stretching and bending vibrations, stretching absorption of bond appear at higher frequency or higher energy as compared to the bending absorption of the bond. Why? What is the reason? If there are two atoms, let us consider this is a central atom and these are the two subsequent atoms. When something is stretched, when you want to stretch something and when you want to bend something, bending like this and stretching like this, more energy is required to stretch in comparison to bend. So, a stretching absorption of bond appear at higher frequency as compared to the bending vibration of the bond. Now, we are going to discuss here the molecular vibrations in a simpler form, stretching vibration. They are stretching vibration is two types, one is symmetric and other is asymmetric. Let us consider these are the two atoms attached with the central atom. In general, in stretching vibration, these are two atoms and this is a central atom. In case of stretching vibrations, either the distance, either both atoms either move away from the central atom or it comes closer to the central atom. It means either it stretches or it compresses just like a spring. In this case, you have learned that bond length changes, but bond angle remains the same. We are going to discuss with the help of types of stretching vibration, symmetric and asymmetric. In the case of symmetric vibration, two atoms with respect to the central atom either stretches or either compresses. It means either bond length increases or bond length decreases. While in the case of asymmetric vibration, when atom stretch, other is compress, or it means when one atom moves away from the central atom, other atom comes towards the central atom, or when it comes towards the central atom, it moves away from the central atom. In this case, you have also noticed that there is change in the bond length. We discussed in this previous slides about the stretching vibrations, and in which we discuss about the symmetric stretching and asymmetric stretching. In the symmetric stretching, bond length increases or decreases with respect to the central atom, while in case of asymmetric, bond length of one bond increases and the bond length of the other bond decreases. Now, come to the bending vibration. Bending vibrations, as we earlier discussed, in this two atoms bend with respect to the central atom. Either this will move like this or this will move like this, but they bend like this way or this way. It means there is change in their bond angle, but bond length remains the same. Molecular vibrations are four types. Scissoring, rocking, wagging, twisting. Scissoring, rocking, wagging and twisting. Let us consider these are the two atoms attached with the central atom. Second type is bending vibration. Bending vibrations are four types. Number one is scissoring, second is rocking, third is wagging, and the fourth is twisting. Now, in case of bending vibration, we have seen these are the two atoms attached with the central atom. Two atoms either bend towards left side or bend towards the right side. In this case, in the case of bending vibration, you have seen that there is change in their bond angle, but bond length remains the same. Out of the four types of bending vibrations, two vibrations are in plane vibrations and two vibrations are out of plane vibration. Out of plane vibration. In the case of, first of all, we are going to discuss about the scissoring vibration. In the case of scissoring, out of the four types of vibration, these two vibrations are in plane vibration and these two vibrations are out of plane vibration. Now, first of all, we are going to discuss about the scissoring vibration. This is the central atom attached with the next adjacent two atoms. In the case of scissoring, two atoms moves in a opposite direction. just like scissor. You have know the function of scissor, both the ends move in a opposite direction like this, but in this case also both the atoms move in a opposite direction. The second type is rocking. Again, this is the central atom attached with the next two adjacent atoms. In this case, both the atoms move in the same direction, either bend in this direction or either they bend in this direction. And the third one is wagging. Same central atom attached with the two adjacent atoms. In the case of wagging, both the atoms either move above the plane or either they move below the plane. Either they move above the plane, both atoms simultaneously, or below the plane, so that they change in their bond angle. Fourth type is twisting vibration. Same central atom attached with the two adjacent atoms. In this case, if one atom move above the plane, next atoms move below the plane. Either first atom moves above the plane, then other atom below the plane, so that this type of vibration like twist, one move above and other move below the plane. These are the slides of bending vibration which we have done studied in the previous slides. Scissoring vibration, rocking vibrations, wagging and twisting. These bending vibration is also called as the deformation. This is also known as the deformation vibrations. Now, after studying about the molecular vibrations, we are going to discuss about the fundamental vibrations. With the help of these fundamental vibrations, we are able to calculate in different molecules how many bending or stitching vibrations are present. Fundamental vibrations, generally all atoms or molecules have different degrees of freedom. A molecule has many degrees of freedom as a total degrees of its individual atom. Each atom has 3 degrees of freedom according to their axis x, y and z. Thus, in an atom there will be if atom is n, there will be 3n degrees of freedom. In molecules, movement of the atoms are constrained by interaction through chemical bond. There are 3 degrees of freedom: rotational, vibrational and translational. Translational, in the case of translational, there are 3 degrees of freedom. In case of rotational, there must be a linear molecule and non-linear molecules. In the case of linear molecules, in case of translational, there is a 2 degree of freedom, while in case of non-linear molecules there are 3 rotational freedom. With the help of these, we are able to calculate the number of vibrations present in a given molecule. Fundamental vibration we can easily calculate. Let us consider this is your total degree of freedom 3n. We are going to discuss first for linear molecules. There is translational freedom plus rotational freedom plus vibrational. Translation, there is 3 freedoms: In the case of linear molecules, only 2, and with the help of this we have to calculate the number of vibration, which is 3n minus 5. With the help of this we can able to calculate the fundamental vibrations in case of linear molecules. Likewise, for non-linear, there's n is number of atoms for translational plus rotational plus vibration. In the case, there are 3 translational freedom, 3 rotational in case of non-linear, and with the help of this we have able to calculate the number of fundamental vibrations in case of non-linear molecules, and the formula becomes 3n minus 6, which is shown in this particular slide. With the help of these formula for linear and non-linear molecules, we are able to calculate the number of fundamental vibrations in any molecules. For example, carbon dioxide, this is the linear molecule, and the number of atom in this molecule is 3 atoms, and the formula for the linear molecule is to calculate the number of fundamental vibration is 3n minus 5, 3 into 3 minus 5, it means 9 minus 5, it is equal to 4 fundamental vibrations in case of CO2 molecule. Taking another example of non-linear molecules. For example, benzene is non-linear, total number of atoms in benzene is 12. With the help of the formula molecular vibration, the formula is 3n minus 6, 3 into 12 minus 6 yani 36, it means 36 minus 6 is equals to 30 vibrations in case of the benzene molecule. So, with the help of these linear and non-linear method for calculating fundamental vibration, you can able to calculate or infer the number of fundamental vibrations in any type of molecules. Now, we are going to discuss the selection rule. Selection rules means this signifies that with the going through the selection rule, which molecules are able to absorb IR absorption, or not all molecules absorb IR radiation, only those molecules which have change in dipole moment or there is a dipole moment present in the molecule show absorption in the IR region. IR active bonds. Not all covalent bonds display bands in the IR spectrum, only polar bonds do so. These are referred as IR active bonds. Like the same way, IR inactive bonds. IR inactive means those molecules when placed in the IR radiation range, there is no change in their dipole moment. It means they are referred as the IR inactive molecules, but the selection rule for the IR is the molecule should have the dipole moment, or if it does not have dipole moment, but when placed in the IR region through the molecular vibration there is change in their bond length. So, dipole moment is developed. Strongly polar bonds such as carbonyl groups produce strong bands. Medium polarity bands and asymmetric bonds produce medium bands, while weakly polar bands and symmetric bonds produce weak or non-observable bands. These are the strong carbonyl, these are the medium and these are the weak, and these are in these compounds the IR absorption is not absorbable. Number of vibrational modes. As we discussed earlier, for non-linear molecules, number of types of vibration is 3 n minus 6. For linear molecules, types of vibration is 3 n minus 5. With the help of these examples, this is your HCl and this is the example of CO2 which we earlier discussed. These are the two conditions which is necessary for absorption in the IR region. There are two conditions on the basis of which molecules show absorption in the IR region. Number 1, incident frequency is same as the frequency of the vibrating molecule, then these molecules show absorption in the IR region. And the second condition and the most important is there must be their net change in the dipole moment of the molecule. We have gone through the theory of the IR spectroscopy, in which we learned about the molecular vibrations, we learned about the fundamental vibration, how we calculate the fundamental vibrations with the help of simple formula. If you have any queries regarding this topic, please you may contact in my email ID. Thank you.